The next question is, how can we calculate the eigenvalue? How do we find the eigenvalue? We have to start with our eigenvalue equation, which is matrix times eigenvector is equal to eigenvalue times eigenvector. What I will do now is I will subtract this side and bring each part onto the same side. So now on the right hand side I have a zero vector. On the left hand side I am multiplying my matrix times vector and subtract my eigenvalue times vector. Now I have the same factor, the eigenvector, on both my parts here. So I want to isolate that. Then I will have matrix minus number, which I cannot do. So what I am doing here is I'm multiplying with 1. The 1 in the sense of the matrix is the unit matrix. So I'm multiplying with the unit matrix, and now lambda times unit matrix is an n times n matrix, just like A is an n times n matrix. And if I isolate the eigenvector, I get so isolating mu gives me A minus lambda times 1 unit matrix times mu is equal to 0 vector. There are possible solutions for this. Either my eigenvector could be 0. This is actually not the case. An eigenvector can never be 0. So the 0 must be in this matrix term. Being a linear map, this matrix term does not have to be the 0 matrix. It is fully sufficient that this matrix has a determinant value of 0. So to fulfill this equation, I need the determinant of A minus eigenvalue times unit matrix to be 0. This will fulfill this equation. The determinant, of course, is a polynomial. This will be a polynomial of grade n in lambda. The name of this polynomial is the characteristic polynomial. You might remember this term from the solving of linear differential equations of second and higher order. That's not a coincidence, but this is exactly the thing that you need to solve these linear differential equations, and we will come to that not today but later as well. So the determinant, the characteristic polynomial, the polynomial is a polynomial of grade n for an n times n matrix A. What does this mean? This means that we will have n solutions, and these solutions will either be single, simple solutions, it will be multiple solutions, one solution that appears more than once, or it will be pairs of complex conjugate numbers. So, having up to n different or not different solutions, we can have a look at those solutions. If we find an eigenvalue of 0 or more than one eigenvalue equal to 0, then the matrix cannot be diagonalized. If all eigenvalues are different, if we only have single solutions or pairs of complex conjugate, then the matrix can be brought into a diagonal form. And if we have some multiple solutions, some lambdas which are the same, then we cannot say if it can be diagonalized or not. And this is also beyond the scope of this lecture. If you come to this situation, then you go and ask a mathematician. So if we now look at the set of all eigenvalues, you will also often find the word spectrum, which is the set of all eigenvalues. This again gives an idea of how the Fourier analysis and the eigenvalues and eigenvectors are connected. And you should keep in mind that while 0 is a possible eigenvalue, 0 is not a possible eigenvector. You cannot have the 0 vector. That would always be the solution where the determinant is not vanishing, and you could not then calculate, or you would not get the characteristic polynomial. 0 as the eigenvalue, on the other hand, is a possible solution.